talks about the forces, and it asks you to draw a free body diagram, and it wants you to consider that you've got this situation in which the dart is going to strike to and stick to the bar. And so they ask you to draw arrows representing the forces. Be a little careful here. I think there's definitely wrong answers here. The dart's going to push on the bar with, I don't know, force from the dart. But there's going to be a force on the bar from the thing it's mounted to, the axis of rotation. So this arrow should be drawn, and it should be the same size as the force from the dart. If it's not, then this whole thing would move in whatever direction the net force was, but it doesn't move, it spins. So I think the two arrows probably need to be made the same size. I doubt you'll get full credit if they aren't. And they need to be drawn where we see them, which is where they act. So we know that the dart pushes down, and we're looking down on this, but the dart pushes down on it. In order for it to not move anywhere, there needs to be a force upwards on it so it doesn't change location, it just spins. And the reason it spins and doesn't, the reason why it spins, it should be clear that this force doesn't apply a torque because it's at the center. Any questions about that? Yep. So our next job is to figure out the velocity of the dart. So we have this situation first with the dart traveling at, they say VI for V initial. And then let's go ahead and advance to what happens next. The dart hits the bar, and the dart and the bar spin. So there'll be an angular speed here. So this screams that this is a conservation of angular momentum because it's a collision question. One thing is hitting another. So that's where I'm going to start. The dart has angular momentum. I'm going to use that point mass angular momentum formula. That's where I'm going to start, but I'm going to populate it with the stuff it told me to use. So it said to use R as the distance from the pivot point to where the arrow strikes. So I'm just going to use R. And then it told me to use MD for the mass of the dart. And then it told me to use VI for the initial velocity of the dart. This has to be the angular momentum of the dart. Any question about that? I'm sure that's probably going to be worth a point or something like it. The next one is we have to come up with the angular momentum of the system after the collision. Well, the dart and the bar are stuck together now, so they have a combined moment of inertia. There's the moment of inertia of the bar, which I think we just are supposed to use IB, okay. And then there's the moment of inertia of the dart, which we use a point mass for. So that's got to be MD times R squared. But we have to use the same R here, lowercase r, because it's a lowercase r away from the axis of rotation. Don't put a capital R here. When you look at the variables you're allowed to have in your answer, the capital R isn't among them. Now this is going to be times omega, except we don't actually want omega, do we? We want the velocity of the dart, and the dart's got a linear velocity here, V final. That's a bridging equation. We're going to need to have a bridging equation to figure out what the linear velocity of the dart is. We know that this whole thing will have an angular velocity of omega, but we're going to have to replace this with V final over R, because we're going to need to use that relationship here to figure out the velocity of the dart. Don't be fooled by something like this. You guys, we've done this a bunch. That's not enough. You got to put it all together to get an actual answer. That part's not particularly hard. We're just going to set this equal to that. And there's not a whole bunch of math here. I'm going to multiply both sides by r and put an r squared over there. And then I'm going to divide out both sides by IB plus MDR squared. So IB plus MDR squared. I'm going to rewrite this so it's a little neater, and I get VF equals RMD R squared. Oh, just R. Sorry, not R squared. Oh, yeah, it's R squared. I'm sorry. I multiplied both sides by it. Mr. Shelton, do better. Be a better teacher. Okay. Probably not going to happen today. There. That's all of this rewritten there. Then underneath, I for the bar plus mass of the dart times R squared. There. That's the answer. You can't cancel out the R's on top and bottom. Some people asked about it for our sixth period, but you could only do that if every term had it in there and every term does not. The next question has to do with something else here, but are any questions about this part? Yep. I didn't cancel it. I multiplied both sides of the equation by it. That turned this from r to r squared. That okay? All right, so then there's another part where they ask about two different bars. One that more or less looks like this. And one that looks similar. Yeah, really? But something like this. And they say that we have a similar situation where a dart is going to strike at the edge on one of these, or both of these. And you have to figure out in which case is it going to have the faster spin after the collision. And they say that the still has a fixed axis of rotation. I think if you want all the credit, there's a couple things you have to be able to say. First, is it clear to you that one of these is going to be harder to turn than the other? Is it the one that's on the right or the one that's on the left that's harder to turn? Yeah, this one. This one is harder to turn. Bigger moment of inertia. So if you want to get full credit, I think you're going to have to say that the angular momentum of the dart is the same in both cases. Remember, you have to explain what's the same. You always forget that part, but don't. That's a point. So I would say the angular momentum of the dart is the same in both cases, which means the angular momentum of the system is the same in both cases, because nothing about the dart is changing, and that's the thing that has the angular momentum before the collision. And it's going to be the angular momentum after the collision. So the angular momentum of the system is the same in both cases. But the moment of inertia is bigger for one of these than the other. And I don't think that'll be enough. I think I'll have to explain that's because the mass is further to the edges than the middle. I think I'll have to explain how you know that the moment of inertia is greater. And after that, you just have to give an implication. What does that mean? And I would just say if the moment of inertia was greater, the object's harder to turn. I think that's sufficient. You could say that if you look at the equation that you just derived, moment of inertia is in the denominator. So if it gets bigger, the velocity gets smaller. You could point to the equation, but if you don't feel comfortable doing that, then say it in plain language. Something that has more inertia is more difficult to turn. All right. Let's go try the next one. Faster or slower? When they walk to the edge, is it going to go faster or slower? Slower, yeah. It's got more inertia. Does the angular momentum change? No, the angular momentum will stay the same. But because the moment of inertia goes down, angular speed is going to go up. So they want to know, of course, an expression for the final angular speed. So it's going to be the angular momentum before they walk to the edge equals the angular momentum after they walk to the edge. Now, for those of you who are having a little bit of difficulty understanding this one concept, they are a point mass. So their moment of inertia is going to be mr squared, where r represents the distance from the axis of rotation. This has a mass of d for disk, and they are what, mp for person. So let's start at the beginning. Their moment of inertia will be the mass of the disk times 1/2 times r squared plus the person, which is going to be mp times 0 squared. They're at the axis of rotation, so they do not contribute anything to the inertia. So that's where we start. Now that has to be equal to the angular momentum after they walk to the edge. So we're still going to have two parts to the moment of inertia, but one won't be 0 this time. The disk doesn't change, but now the person is at the edge. You can be able to do this tomorrow? Oh, man, I'm hoping. Now, we're not done. We have to solve, but I'm going to go ahead and just remind myself that that's going to be 0. And to solve, we just need to divide both sides by all of this. That good? Are you okay doing this? You guys can do this? I hope. Now, I do want to say this is probably the bulk of the points, but it's not all of it, because they're going to ask after this, does your equation agree with what you wrote earlier? And remember, they talk about functional dependence. So you would have to say something like, if something in the denominator gets bigger, the number gets smaller. And we have something in the denominator here that wasn't there before. So the denominator is going to get smaller because of the person's inertia. So yes, it agrees. Because we said it'd get smaller, and this would make it get smaller. By the way, this is a situation where you could cancel out all the r squareds. You could, because it's in every term. So that would be just fine. I don't think you're doing anything wrong by leaving it, but you could cancel out all the r's. Take a look at this for a minute. I couldn't find an example of this in my AP, but there's a lot of examples of these, and there's one in the homework like this. This can be a conservation of angular momentum thing too. Old style record players did this. So imagine the bottom one is spinning. If we drop the top one onto the bottom one, will the system speed up, stay the same, or speed down? Meaning, will it spin faster if this drops on there, stay spinning the same speed, or slow down? I'm not trying to trick you. What's going to happen to the inertia of the system when we drop the top plate onto the bottom plate? What's that? You can mumble all you want, but tomorrow's your test. So if you don't know the answer, say, I don't know, Mr. Shelton, and let's move on. Well, you better pick up on this. This has inertia, doesn't it? Because it's got mass. And if you're going to drop this one thing that's not spinning onto something that is spinning, there's going to be a time where the bottom plate is slowing down because the top plate is scraping on it, and the top plate is speeding up because the bottom plate is spinning under it. They will eventually come to the same speed. This is a conservation of angular momentum question. This is the only thing with momentum before. But then, when the top plate drops to the bottom plate, they're both going to come to some final speed. It will be slower.